Welcome. Today we're formally discussing word problems. We are going to define density and mass and work and forces. And first up, we're going to talk about density. Now you probably are familiar with mass is equal to density times volume, and this works as long as we have uniform density. When we don't have uniform density, we're going to have to use calculus. And once again, we'll use the slice and dice method. We'll slice up our object, we'll slice it into an infinite number of pieces, and then we will take that density function that we have and multiply it by the width of our slices, and we're going to let that width go to 0, and we're going to add all of that up so that we can get our mass. So first up we have a 2-meter bar. That means along the x it goes from 0 to 2. So my integral would go from 0 to 2. I need my density function, and this density function is in the units of kilograms per meter. So 1 plus x squared dx. Then I'm just going to integrate this thing. I'll then end up with 14 over 3 kilograms. Just doing my little computation there. On to the next one. Next up we have work. Now work is equal to force times distance. That's something you're probably familiar with. But now let's look at work as our force varies. So we're not going to push with a uniform force, or whatever is acting on that isn't with a uniform force. It's a force that is a function. And similarly, what we're going to do is take that force function and we're going to slice and dice it and add up over that interval. Okay, we're looking at Hooke's law, and we have a force of 10 Newton. Now Hooke's law is F equals kx, where k is our spring constant. So it's this spring constant that we have, and it's a spring constant that will be, as long as you're using that same spring, that spring constant stays the same no matter what. So our first order of business, A, is to find that spring constant. Well, if F equals kx, and we have 10 newtons here, k, and 0.1, our units are all good because that's in newtons, that's in meters, and I'll just do that division and we will get k equals 100 newtons per meter. Well, this will allow me to do the rest of the problems, because I now know that my force function f of x equals 100 times my x. So for question B, how much work is needed to compress a spring? So work equals, and they want to know from 0 to negative 0.5 because I'm compressing, and I would just do 100x dx. Pretty straightforward integral. I'll have 100x squared over 2 evaluated from negative 0.5 to 0, and with that you'll end up with 12.5 joules. And the rest of them are very similar. I'll just go ahead and write down the setup and whatever for the rest of them. Okay, C was pretty straightforward, just wanted to know from 0 to 0.25. In D, they wanted to know how much additional work is required to stretch the spring 0.25 meters if it's already been stretched 0.1 from equilibrium, so they just mean for you to go from 0.1 to 0.35, and same integral computation on all of them. Fairly straightforward on that one. Alright, this next problem is another work problem. This time we are moving something upward. We're lifting. In that case, we're going to need our gravitational constant here. We're also, if we're moving water, then we're going to probably need this guy right here. Most everything we deal with is going to be in meters and in kilograms, so we'll need that. In this particular tank, we are moving the same area of disk up and out. So that's going to make this one, it's going to simplify this a bit, because our area as a function of y is going to be a constant. The shape of that tank doesn't change. Now if that was a cylindrical tank laid on its side, then it wouldn't stay constant, but in this case our radius is 5, and so it's just going to be pi times 5 squared, which is just 25 pi. And that makes that nice for our work problem. On this work problem, the amount of fluid is from 0 to 10, and then our density, so I'm using this formula here, our density is 1,000. I already have my units coherent, so I'm not going to put those in, times 9.8 times 25 pi. Now our distance, this d of y, this is going to be the distance that each of these slices must be lifted. And this distance, you know, this bottom slice has to be lifted 15 all the way up here to the top. So this this distance formula is this d of y, d of y is going to be the 15 minus y. So I'm going to write 15 minus y for that distance that they must each be lifted. So notice that the disk here on the bottom at y equals 0 has to be lifted 15. The disk here, say at 2, has to be lifted 15 minus 2, 13, and so forth. And now this is just an integral computation. The hardest part of this is just setting it up. Once you get finished computing that, you'll get 7.7 times 10 to the 7th joules. This one introduced a variable area, because this area changes as I go up and down the tank. If it would have been sitting on its end, it would have been just like the other problem, but it's not. So now I need to know what's the work required to take this amount of gasoline out of the tank. And it is coming just through an outlet at the top of the tank, so it's going to be moved up through that distance of 5 there, and depending on where it is in the tank. And I believe this tank has a radius of 10, so this top layer would move 5 and the bottom layer here would move 10. Now it's going to be most convenient to go ahead and make our y equals 0 right here at the middle of the tank, so that I can have the symmetry as I go up and down here. That means that for my limits of integration, that's going to be -5 to 0 is going to be where this is the interval that this is going to move from. The density they gave to us, that's a constant. I like that one. That is 737, It's in kilogram per meter cubed, so I'm good with that. The gravitational constant 9.8. The area as it changes with respect to y, this one is not quite as pretty. However, I know that this area of this rectangle is going to be whatever this x distance is here, and times 2 because it's some on either side. So I've got this x distance, but you know, this x is just the equation of a circle, and there are two of those because this x distance wouldn't just be this one x, but it would be this x and this x. So I'm going to get that my area is 2 times that radius, and then because it is a rectangle, the length of that rectangle is 10. So that's my area function, so it will be basically 20 times the square root of 25 minus y squared. Then the distance that it's going to be moved is just 5 minus whatever this y distance is here, and then dy. And then I'm going to move my constants out front, and I believe I can use substitution in my integral here, so I'm going to give that a try. Oh man, that got long and messy. Let's see. So I went ahead and distributed this square root to both those two guys. Then I used my tables because this was a perfect form in one of the tables in the back. So I used my table, and that thing actually condensed to 125 pi over 4, that whole big left hand one. And then the right hand one I just used substitution here, and then ended up with this really at the end it was just 25 to the 3/2 power over 3. And there's my exact answer here, and then here's my approximate, and that'd be the number of joules. The next topic that we're going to deal with is hydrostatic pressure. We're referring to the force of a body of water or some sort of fluid on another surface, and we're going to find that pressure or that force of that body of water. Now, force and pressure are related, and that pressure equals force divided by area, and you can see that this pressure can then be derived to give density times gravity times height. So let's work a problem. Here we have our formula that we're going to be working from. Force equals, and this is from the bottom. Now, one of the hard parts about this is setting these problems up. This has kind of been done for us where we said just we're going to have this so that it's symmetric. We're going to put it in the center just like we did the tank in the last example, and this means that our force is going to go from 0 to 30 because that's the height of this dam. Then I've got rho times gravity, it's water, so my rho is going to be 1,000, gravity is going to be 9.8. Now the depth of the water, it's going to vary from 30 down to this 0, so it's going to be similar to the others, 30 minus y, depending on where we're at. And then the harder part here is to figure out the width of this. Well, I have 2 points, and since I have 2 points, I can write the equation of that line. And here's the equation of the line right here. Just using, just general techniques to find the equation of the line. Well, I need this in terms of y, so I just rewrite this in terms of, so that my function is in terms of y. Now that would be any x distance from here to here, but it goes all the way across, so it wouldn't just be one of those x's, it would actually be two of those x's. So it would be two of these 1/3 y plus 30s. And then dy. And once you've got this set up, now it's just a matter of manipulating this and integrating. After integrating this, which is fairly straightforward problem, you get about 1.18 times 10 to the 8 newtons of force. And that concludes section 6.7. Hope to see you at the collaborates.